Hello, Matayom students. I am recording this video so you can watch this again and again with a Thai translation on YouTube so you can prepare for your final test. Okay? This will save your time and your effort in studying the lesson if you study this consistently every day. So now our lesson is on Science chapter 6 about heat, but specifically on the topic of effects of heat on matter. This is the first part of this lesson. This is a big topic, so I want you to translate your books ahead of time, those words which you really don't know, so you can actually understand better. When you see the translation here, it will just help you. So right now, effects of matter or effects of heat on matter. When matter gains or loses heat, it will undergo some changes such as expansion or contraction and changes in temperature and then changes in states of matter. Now, what about expansion and contraction of matter? Most matter expands when heated and contracts when cool. One common example of the effects of heat is a thin glass cracks when hot water is poured into it. So the increase in the size of objects when they are hot is called expansion. The decrease in the size when they're cooled is called contraction. All right? So, now, what about the expansion and contraction of solids? The arrangement of particles in a solid is like this. So you have this cold and you have this, when it is heated, it moves like this. So the atoms or molecules in a solid vibrate at all temperatures. Okay? As its temperature increases, the atoms vibrate more vigorously, and these vibrations push the atoms further apart. So the volume of the solid increases, and so the solid expands. All right? Now, look at the expansion and contraction of solids. Look at here. So the atoms or molecules in a solid vibrate at all temperatures, as I said, but as its temperature decreases, the atoms vibrate less vigorously and become closer. You see, the volume of the solid decreases, and so the solid contracts. So when the molecules, hot molecules, are cooled off, they move like this so slowly when already cold. All right? Now look, what about when they are cold like this? And then when heated, look at them. So molecules in liquids glide in another. When a liquid is heated, the molecules of the liquid have more energy and move more vigorously. Okay? So this allows them to have greater freedom to move over greater volumes. Thus, the liquid expands. All right? Okay. What about the arrangement of particles in a liquid? When it is hot, look at the movement. All right. When it is cool, it looks like this. So molecules in liquids glide in another. When a liquid is cool, the molecules of the liquid have less energy and move less vigorously also. So this allows them to have lesser freedom to move over lesser volumes. Thus, the liquid contracts. All right. Now, so what about the expansion and contraction of gases? So the molecules of a gas are far apart compared to the molecules in a solid and a liquid. The gas molecules move at a high speeds in all directions. If a gas is confined in an expandable container, the volume of the gas will increase with increasing temperature. The volume will decrease as the temperature drops. All right? Now, look at the arrangement of particles in a gas. When the gas is heated, The molecules become more energetic, move faster, and are farther apart. This causes the volume of the gas to increase and expand is said to occur. Okay? So look at the movement here when heated. This is the reaction and the action. All right? So, what about the arrangement of particles in a gas? When the gas cooled, the molecules become less energetic. They move slower and are closer. This causes the volume of gas to decrease and contraction is said to occur. All right? Now, we don't need to learn more on this thermal expansion and contraction of matter from the source because it's just about the same idea anyway. Now, hot tips. Always remember that the particles themselves do not expand or contract when heated or cold, right? Or cooled, I should say, when heated or cooled. Now, let's observe this activity, expansion and contraction of solids, all right? So we need some materials like metal ball, metal ring, and Bunsen burner. And the procedure is this, all right? A metal ball is dropped through a ring as shown in the above figure. And then the ball is taken through the ring and heated over a Bunsen flame for a few minutes. Then it is dropped through the ring again. Okay, so the ball is allowed to cool down to room temperature and is dropped through the ring again. And so what can you observe? All right, now you see before heating, okay, and this is after heating, the metal ball cannot pass through the ring when it is hot, but when it is cool, it can pass through the ring. Okay, so right here, discussion. The hot metal ball cannot pass through the ring because the size of the ball increases. This shows that the metal ball expands when heated. The volume of the metal ball increases. When the metal ball cools down, it contracts back to its original size, and so it can go through the ring again. The volume of the metal ball decreases. Conclusion: solids expand when heated and contract when cooled. I think this is so clear, right? Let us watch this video so you can actually understand better. All right? Okay. I want you to watch this on here. I hope this is clear for all of us. But let me expand that on YouTube so that you can even watch with a better resolution. All right.
Most people over 40 will enter 2026.
Post this video right here. Pause the record.
Expand on heating and contract on cooling. Take an iron ball and a ring apparatus. At room temperature, the ball just passes through the ring as shown here. Heat the iron ball. Now try to pass the ball through the ring. The ball does not pass through the ring. Why is this so? When the ball is heated, it expands and its size increases. After some time, when the ball cools, it contracts and will again pass through the ring. This activity shows that solids expand on heating and contract on cooling. Take a metal bar and a gauge as shown here. Try to fit the metal bar into the gauge. The bar exactly fits into the gauge. Take the bar out and heat it for some time. Now try to fit it into the gauge. You will see that it does not fit at all now. The reason is that the bar has expanded due to heating. Let the bar cool for a while. As soon as it comes to its original temperature, it again fits into the gauge. This activity shows that solids expand on heating and contract on cooling.
Imagine being able to build an app with your name on it, just by thinking about it. Meet
Now that we have watched it, let's talk about the expansion and contraction of solids. So another one, we need materials like thermometer, beakers, ice, and hot water. And how it is to be done? Here's the procedure. A thermometer is placed inside a beaker of hot water as shown in the figure. The movement of the mercury column is observed and the highest temperature is recorded. And then the thermometer is taken out and placed in a beaker of cold water. The movement of the mercury column is observed again and the lowest temperature is recorded. And so what can you observe? Here's the observation. The mercury column rises when the thermometer is placed in the hot water. The mercury column falls when the thermometer is placed in the cold water. Now, what can you discuss? The discussion is that the rise of the mercury column is due to the increase in volume or the expansion of the mercury, which is liquid. The fall of the mercury column is due to the decrease in volume or the contraction of the mercury. The conclusion is that liquids expand when heated and contract when cooled. All right, what about the expansion and contraction of gases? Now we need these materials, a round bottom flask, glass tube, rubber, stopper, indicator, and retort stand. What's the procedure? We need this one. Number one, the apparatus is set up as shown in the picture. The original position of the colored water column in the glass tube is also marked. Number two, you rub your hands and place them on the flask to heat the air in the flask. The movement of the colored water column is observed. Number three, remove your hand from the flask and the flask is allowed to cool down. The movement of the colored water is observed again. Now, the observation is that the colored water column is seen moving upwards when the round bottom flask is held by the warm hands and moving downwards when the flask is allowed to cool down. Discussion. So the rise of the colored water column is due to the increase in the volume or the expansion of the air inside the flask. The fall of the colored water column is due to the decrease in the volume or the contraction of the air inside the flask. So what is the conclusion? Gases expand when heated and contract when cooled. Now let's watch this video again so we can understand even more.
When a solid is heated, it expands. When it is cooled, it contracts. When liquid is heated, it expands. When cooled, it contracts. As When a solid is heated, it expands. When it is cooled, it contracts. When liquid is heated, it expands. When cooled, it contracts, as can be seen in a mercury thermometer. Is there a way in which we can see what would happen to air when we heat it and then see what happens when we cool it? Let us take a look. For this, we need spirit lamp, cold water, test tube with rubber cork, straw, and colored water. First, we will trap a drop of colored water in a straw. Insert the straw through a rubber cork, like this. Now put the cork in the test tube and make sure no air escapes. Now heat the tube and observe the colored drop. The drop rises. Cool the tube in the beaker filled with cold water and observe the drop. The drop comes down. You will see that the drop of water moves up when the tube is heated and it comes down when it is cooled. The water drop rises because air inside the tube expands on heating. The expanded air pushes the colored water drop in the tube upwards. When the air cools down, it contracts and the drop comes back to its initial position. So we just saw that air expands on heating and contracts on cooling, just like other materials. Now, expansion of air on heating causes its density to lower. On the other hand, contraction of air on cooling causes its density to increase. This change in density of air on heating or cooling is the principle behind the hot air balloon. With increased flame, the balloon starts slowly going up, and with decreased flame, it starts slowly descending to the ground.
It looks like my brother, right? We both have baldy head, right?
When a solid is
Okay.
heated, it
I hope that's clear for you right now. Now, we don't do the workbook because you don't have it. So let's talk about the uses of expansion and contraction of matter. So the effect of expansion and contraction of matter can be very troublesome. Precautions have to be taken against these effects. We can also apply the principle of expansion and contraction of matter in making instruments that are useful in our daily life. Okay? So the following are some examples to show the uses of expansion and contraction of matter. A. Mercury in a thermometer. Mercury is a liquid metal that can expand and contract when there is a change in temperature. This makes it suitable for temperature measurement, and it is used in a thermometer. You see that one here? Look at that. How mercury helps us understand between the expansion and the contraction. All right? Okay. Now, what about the bimetal, we call this bimetallic strip in a fire alarm? Here's a bimetallic strip. All right? This one. So an automatic fire alarm uses a bimetallic strip to switch on the electrical bell when there is fire. The heat from the fire causes the bimetallic strip to bend towards the contact point, I should say. Okay? So when the bending strip touches the contact point to complete the circuit, the fire alarm rings. Ring! All right? So that is the idea of the bimetallic strip in a fire alarm. What about the bimetallic strip as a thermostat? The bimetallic strip is also used as a thermostat, okay, in an electric iron for controlling and maintaining temperature. As temperature rises, the bimetallic strip bends away from the contact point and cuts off the current. Okay? So you see how it works. This one, like this. So when the iron is hot, it goes up, it bends away from the contact point and cuts off the current. Wow. Now we know why your iron is cool or hot. Okay? So it's the contact point. Next, what about in this? When the metallic strip cools down, contact is made again and current flows once more to heat up the iron. What about a bimetallic thermometer? A bimetallic strip worn in a spiral can be used to make a thermometer. In the figure below, the metals used are brass and invar, with brass on the outside. As the temperature decreases, the spiral is wound tighter, okay? And the pointer will move to the left. All right? You understand? Okay. What about the metallic tires? The metallic wheels of a train are fitted with metal tires to ensure a tight fit. The tire is made slightly, I should say, smaller in a diameter than the wheel. Before fitting, the tire is heated uniformly, and the resulting expansion enables the tire to be slipped through the slip over the wheel. Upon cooling, the steel tire contracts and makes a tight fit. Wow, this is it. So wonderful. Now, removing metal lids. A very tight bottle cap can be removed easily by immersing it in hot water. Okay? So the cap expands much faster than the bottle. So the cap can be removed easily when it expands. You understand? This is hot water. It's submerged in a hot water, so the metal lid expands and be easily removed. Now, fixing the axle into the hub of a wheel. All right? So the hub of a wheel is usually slightly smaller than the size of its axle. To fix the axle into the hub of the wheel, the axle has to be put in a liquid nitrogen at minus 190 degrees Celsius to cool it so that it contracts until it can be fitted into the hub. So this is smaller, this is bigger, right? So it has to cool down to fit into this. So this is fixing the axle into the hub of a wheel. What about the rivets? The rivets are still pins used to join pieces of metal tightly together. They are heated before being inserted through the pieces of two pieces of metal. While the rivet is still hot, the end is hammered, okay? Flat, all right? And then look at that one. It's hammered and it looks like this when the rivet is still hot. So when the rivet cools, it contracts, pulling the two pieces of metal slightly together. All right? I think you understand better. Now let us watch this example of thermal expansion in liquid. All right? Okay, here.
Have you ever rubbed metal continuously with the surface? If so, you would have noticed that metal gradually changes its shape. It expands, therefore, there is change in either its area, volume, or shape. Even when iron is exposed to heat, it expands. These are all the effects of thermal expansion. So, what is thermal expansion? It is a process in which a body expands in either area, volume, or shape when heated. Thermal expansion occurs in solids, liquids, and gases. First, let's consider solids. When a solid is heated, it expands in size and shape, resulting in an increase in length, area, or volume of the solid. This is known as a thermal expansion of solids. But what makes a solid expand? When a solid is heated, the molecules that make up the solid begin to vibrate. This takes up more space and the solid matter expands. Let's see an example of expansion in solids. When you can't open a tight jar, it is recommended that you place it under hot water for a minute. The metal lid will expand because it heats up and won't be so tight anymore. Now, you can open it easily. Next, let's study thermal expansion in liquids. Like solids, liquids also expand when heated. However, since liquid particles are usually less tightly bound to other particles, they generally move further than solid particles when heated. Hence, liquid expands more than solid when exposed to the same temperature. In a thermometer, mercury is an example of expansion in liquids. When we increase the temperature, the mercury starts to expand, and we can clearly see an increase in the level of mercury. Finally, let us see how gases react when they are heated. Gases expand most when heated. This is because gas particles are far apart and are weakly attracted to each other. It is much easier for them to move further than solids or liquid particles when heated. Heat causes the atoms of the gas to vibrate and take up more space. For example, the gas gauge on a car. People are much more likely to run out of gas in the summer than in the winter. Why is that? Well, the gas in your car expands just like everything else, and it changes the reading on your fuel gauge. In the summer, gas takes up more space in the tank. So, when the fuel gauge reads empty, it indicates that there is significantly less fuel left in the tank than it would be during winter. You may get an extra 35 miles after the fuel gauge shows empty in the winter, but that won't be the case in the summer heat. So, be careful. You don't have to walk 3 miles to the gas station just because you don't know about thermal expansion. Let's summarize what we learned today. Solids, liquids, and gases expand when heated. Thermal expansion causes an object to expand when heated. Gases expand most when heated.
Right, that's interesting, right? Okay, so the following are some examples to show how we solve some problems due to expansion and contraction of matter. About here, A, railway tracks. When laying railway tracks, gaps have to be left between successive lengths of rail to allow for expansion on hot days. Without the gaps, the track buckles, and this affects the safety of the trains. So look at that. Okay? So we have the rail track here, the small gap. This is about a gap in the railway tracks. What about the concrete roads? When concrete roads are laid down, gaps normally filled with bitumen are left between sections in order to allow for expansion on hot days. There should be gaps in between, all right? It's to be filled with bitumen, okay? What about the metal bridges? Structures like steel bridges and overhead bridges are built with gaps to allow for expansion. See the gaps here? Sometimes one end is supported by rollers, which allow the bridges to expand easily when heated. So this one is fixed. This one is not fixed. Okay? What about cables? So electric transmission cable and cable cars, cable sag on a hot day and tighten during a cold night. All right. So this allows, therefore allowances have to be made for the expansion and contraction of the cables. So you see this overhead cable sag in hot weather. Look at the sagging, like that sagging, right? Sag in hot weather and tighten during a cold night. So you got to be careful with this one too. Now, we don't need workbook. You don't have it, but I wanted to answer, right? Go to the next one. Go to the next video and we will see more on the second part of this presentation.